Space seems at first like the one thing that cannot end. A planet can end at its cliff or ocean. A body can end at its skin. A flame can end when its fuel is gone. Space appears to be the stage beneath every ending, the dark room where all events are allowed to happen. It surrounds Earth, surrounds the sun, surrounds every star, every galaxy, every drifting atom of dust. To ask whether space can end feels almost like asking whether distance can die. And yet modern cosmology has made the question stranger than it sounds. The universe has an age. The light reaching us has a limit. The galaxies we see are not simply scattered through an eternal black field. They belong to a cosmic history, a story of expansion, cooling, acceleration, gravity, radiation, and horizons. Space itself is changing. It stretches between galaxies. It carries ancient light toward us. It also carries distant regions away faster than any ship, signal, or civilization could ever follow. So the end of space may not be a wall. It may not be a sudden edge where a traveler arrives and finds nothing beyond. It may be quieter, more mathematical, and far more unsettling. Space may end for the observer before it ends for itself. It may end as reachability. It may end as visibility. It may end as structure, as warmth, as memory, as the ability of one region of the cosmos to know that another exists. The true terror of the question is that an ending does not always announce itself with fire. Sometimes it arrives as distance. The first boundary of space is not a physical border. It is made of time and light. We live inside the observable universe, a sphere centered on every observer, defined by the distance light has been able to travel since the beginning of cosmic history. The universe is about 13.8 billion years old, yet the edge of the observable universe lies roughly 46 billion light-years away in every direction, because space has expanded while ancient light has crossed it. That number already tells us something essential. We are not looking across a still room. We are looking through a moving fabric. When telescopes stare into deep space, they also stare backward. A galaxy seen billions of light-years away appears as it was billions of years ago. A faint red smudge in a deep field image may belong to an era when the universe was young, hot, smaller, and still assembling its first great cities of stars. The most ancient light of all is the cosmic microwave background, the afterglow released when the young universe cooled enough for atoms to form and light to travel freely. It arrives from all directions, a fossil glow stretched by expansion into microwave radiation, carrying the imprint of a universe before galaxies. This boundary can be misunderstood. The observable edge is not a shell of matter around us. It is not the outer rim of all existence. It is the distance from which light has had time to reach us. Beyond it, there may be more galaxies, more clusters, more voids, more regions with their own observers and their own skies. Those regions are hidden because the universe has not existed long enough for their signals to arrive. They are outside our cosmic sight, not necessarily outside reality. For a human mind, this is already a kind of ending. We can map the visible cosmos with instruments of astonishing power, but the map is enclosed by physics. No telescope, however vast, can collect light that has not arrived. No patience can receive a signal that the structure of space-time will never permit. The observable universe is therefore both magnificent and incomplete. It gives us a cosmos wide enough to humble imagination, then reminds us that even this immense sphere may be only a local chamber in a far greater whole. The old instinct is to imagine an edge. A ship travels far enough, passes the last galaxy, crosses the final darkness, and reaches a border beyond which space stops. The image is powerful because human life is built from surfaces. Rooms have walls, islands have shores, countries have borders, bodies have skin. But the universe may not share our local habits. In modern cosmology, space can be finite without having an edge, just as the surface of Earth is finite without offering a cliff at the end of the world. A traveler moving on Earth in one direction never finds the planet's edge. Given enough time and no oceans to interrupt the path, that traveler returns from the opposite direction. The surface is limited in area, yet unbounded. Cosmologists sometimes use this analogy carefully because the universe is three-dimensional space rather than a two-dimensional surface, but the lesson remains useful. A finite universe does not require a wall. It may curve back on itself in ways that are difficult to visualize from within. If space is infinite, then the question changes again. An infinite universe cannot be crossed. It has no far side. It contains every reachable destination as a local island inside a greater extension that never closes. Infinity, however, does not remove endings from experience. Even inside an infinite universe, every observer has horizons. Every civilization has a region it can see, a region it can influence, and a region that drifts beyond possible contact. An infinite field can still become lonely. Current observations suggest that the universe is very close to geometrically flat on the largest scales we can measure. That does not prove that space is infinite. It means that if space curves, the curve is so broad that our observable portion cannot easily detect it. The cosmos may be endless, or it may be so large that its shape hides beyond our horizon. Either way, the absence of a visible wall is one of the great intellectual shocks of astronomy. Space does not behave like a container built for the human imagination. It behaves like a geometry we inhabit without seeing from the outside. This is one of the reasons the phrase "the end of space" is so dangerous. It tempts us to search for a place, when the true answer may be a condition. Space may end as a navigable concept. It may end where information fails. It may end where expansion outruns contact. The border may not stand in front of a traveler. It may exist in the equations long before any ship has moved. The universe is expanding, but this does not mean that galaxies are flying through ordinary space from a central explosion. There is no known center from which everything fled. On the largest scales, the distance between gravitationally unbound galaxies grows because space itself changes with time. The old image of fragments racing outward from a blast can mislead. The more accurate picture is subtler. The metric of the universe evolves, and with it the separation between vast structures. This expansion reveals itself through redshift. Light from distant galaxies arrives stretched, its wavelengths lengthen toward the red. The farther a galaxy is, on average, the more its light has been stretched by cosmic expansion. What began as a signature in spectra became one of the foundations of modern cosmology. The universe is not static. Its grand architecture is in motion. Even the darkness between galaxies participates. For much of the 20th century, scientists expected gravity to slow the expansion. Matter attracts matter. Galaxies pull, clusters pull, dark matter pulls. The great question seemed to be whether the universe contained enough mass to halt expansion and draw everything back into collapse, or whether expansion would continue forever at a slowing pace. Then observations of distant exploding stars revealed a deeper surprise. The expansion is accelerating. The cosmos is not merely growing, its growth is speeding up. The name given to the unknown cause is dark energy. The phrase is humble in the face of ignorance. It does not explain the mystery so much as mark its location. Dark energy appears to make up most of the total energy budget of the universe, and its effect becomes dominant on enormous scales where gravity's local grip weakens. Stars remain bound inside galaxies. Galaxies remain bound in groups and clusters. But beyond those islands, the ocean of space widens with increasing force. This acceleration turns distance into fate. A galaxy far enough away can recede from us so quickly because of expanding space that light emitted from it today will never arrive. This is one of the most haunting ideas in modern science. The universe can contain objects that exist now, shine now, and remain forever beyond future observation. They are present in the same cosmic history, yet sealed away by the geometry of expansion. A horizon is not always a thing. At sea, it is a visual limit produced by curvature and sight. Around a black hole, it is a boundary beyond which escape becomes impossible. In cosmology, horizons are boundaries of information. They define what can be seen, what can be reached, and what can ever influence us. These horizons are among the deepest answers to the question of whether space can end. because they show that the end may depend on the observer. The particle horizon marks the farthest distance from which light has had time to reach us since the early universe. It defines the observable universe. But there is another horizon, more severe and more future-facing: the cosmic event horizon. If expansion continues to accelerate in the way our best models suggest, there are regions of space whose light, emitted today, will never reach us. They are not merely too far for current telescopes. They are beyond all future communication. This means the observable universe is not simply growing into a richer archive forever. Some distant galaxies we can see now will fade from practical access. Their light will become increasingly stretched, dimmed, and delayed. Over immense timescales, galaxies beyond our gravitational neighborhood will appear to slow and redden, their signals thinning into the background. Future astronomers, if any exist in the deep future, may inherit a much poorer sky. Imagine a civilization born trillions of years from now in a galaxy much like ours, long after the cosmic horizon has swallowed the evidence of the wider universe. If its local group has merged into one aging island of stars, and if distant galaxies have faded beyond detection, that civilization may look outward and see only darkness. It may develop physics, chemistry, engineering, and telescopes of great power, yet remain unaware that the universe was once filled with billions of visible galaxies. The cosmos would still be vast, but its history would be hidden. This is an end of space as knowledge. The universe does not need to tear or collapse for the visible cosmos to shrink in meaning. Expansion can erase the evidence of expansion. It can isolate islands of matter so completely that cosmic history becomes unreadable. In that distant age, space will not look infinite and grand. It may look empty, local, and almost static, because the clues to its true scale will have crossed a horizon no mind can follow. There is a difference between what can be seen and what can be reached. Human beings often confuse the two because, on Earth, vision and travel are connected by practical effort. A mountain seen in the distance can be climbed. A city visible across a valley can be entered. In cosmology, sight can be a farewell. We see many galaxies whose future is already inaccessible. Their ancient light reaches us, but no signal sent from Earth today could ever arrive there, even if it traveled at the speed of light. This creates one of the sharpest forms of cosmic confinement. The reachable universe is far smaller than the observable universe. Most of what we can see is already beyond any possible contact. The stars and galaxies filling deep field images are real, but many are images of places no future technology can touch under known physics. They are part of our sky as memory, not destination. The eye receives what the hand can never approach. The reason is the accelerating expansion of space. Light has a speed limit through space, but space itself can expand in a way that increases the distance between regions faster than light could close the gap. This does not violate relativity because galaxies are not locally racing through space faster than light in the ordinary sense. The fabric between them grows. On small scales, gravity wins. On vast scales, expansion rules. For the future of any civilization, this matters more than almost any engineering dream. A culture could master fusion, antimatter, generation ships, suspended animation, and perhaps propulsion far beyond anything now imagined, yet still be trapped inside a cosmic island. The limitation would not be courage, energy, or lifespan alone. It would be geometry. The universe places destinations in the sky that are already mathematically lost. This is a profound kind of ending. Space ends as empire. It ends as travel. It ends as the dream of universal contact. Every year, as expansion continues, more of the universe passes from the realm of potential arrival into the realm of unreachable memory. The boundary is silent. No star flickers when it crosses. No alarm rings in the vacuum. A galaxy simply belongs, from that moment onward, to a region from which no answer can ever come. Even if space itself continues forever, the universe inside it may change beyond recognition. Stars are temporary arrangements of matter and gravity. Galaxies are temporary architectures. Nebula are temporary clouds. Planets are temporary accidents of heavy elements, dust, collision, cooling, and orbit. The cosmic web, with its filaments and clusters, is not a permanent cathedral. It is a phase in a much longer history. The age of stars will end slowly. Massive stars already live brief, violent lives, burning through their fuel in millions of years before exploding as supernova or collapsing into compact remnants. Sun-like stars last billions of years, swelling and shedding their outer layers before leaving white dwarfs behind. Red dwarfs, small and efficient, may burn for trillions of years, far longer than the current age of the universe. They are the long embers of the stellar era. Over time, star formation will fade as galaxies consume or lose the gas needed to make new suns. The universe will still contain matter, but less of it will gather into bright new stars. Galaxies will grow older. Their brilliant blue regions of young stellar birth will dim. The sky will be ruled increasingly by red dwarfs, white dwarfs, neutron stars, and black holes. Light will become rarer, redder, weaker, and more local. Gravity will continue its patient rearrangement. Galaxies in bound groups may merge. Stars may be flung into intergalactic darkness through close encounters. Planetary systems may be disturbed over enormous timescales. Dead stars may cool into black dwarfs, if the universe lasts long enough for white dwarfs to radiate away their remaining heat. Such objects do not yet exist because the universe is too young. The future contains forms of darkness for which nature has not had enough time. In that era, space does not end as size, it ends as scenery. The grand visible universe of luminous galaxies becomes a colder archipelago of remnants. The structures that make space legible to us today, spiral arms, glowing gas, star clusters, nebula, bright stellar nurseries, gradually disappear. A universe can remain physically extended while losing almost everything that once made extension visible. The most widely discussed future under a continued accelerating expansion is often called heat death, or the Big Freeze. The phrase can sound dramatic, but the process is almost unbearably slow. Heat death does not mean that everything suddenly turns to ice. It means the universe drifts toward a state in which usable energy becomes unavailable. Differences fade. Engines require gradients. Life requires gradients. Stars shine because matter is compressed and hot. Weather moves because temperatures differ. Thought itself depends on organized flows of energy. When gradients vanish, action becomes impossible. The universe began in a hot, dense, highly ordered state from which complexity could grow. As it expanded and cooled, gravity gathered matter into stars and galaxies, creating local pockets of structure. Those pockets powered chemistry, planets, atmospheres, and eventually observers. But entropy, the measure associated with disorder and the spreading of energy, tends to increase. Over unimaginable time, energy becomes more evenly distributed. The universe approaches a vast equilibrium where little remains capable of change. In such a future, stars have burned out. Black holes may dominate the mass of the cosmos for a time, slowly radiating through quantum effects over timescales so enormous that ordinary language fails. If proton decay occurs, even ordinary matter may eventually dissolve, though this remains unconfirmed. If protons are stable, matter persists in cold remnants far longer. Either path leads toward a universe where the dramatic events of the stellar age have ended. This is perhaps the most plausible answer to the question of space ending under current cosmological models. Space may not terminate. It may continue expanding into a future with fewer events, fewer lights, fewer interactions, and less memory. The end is not a wall at the border, it is the exhaustion of difference. It is a universe where distance remains, but distance connects almost nothing. For a human imagination trained by days, seasons, and lifetimes, heat death is difficult to feel. It is too slow to resemble catastrophe. Yet in another sense, it is more complete than any explosion. Fire destroys structures but leaves change. Heat death removes the conditions under which destruction and creation have meaning. A universe at equilibrium has no drama left to spend. Space remains as a vast permission, but almost nothing meaningful can use it. There is another possibility, more violent and more speculative. If dark energy is not constant, and if its strength increases with time in a particular way, the expansion of the universe could accelerate so aggressively that it begins to overcome every bound structure. This scenario is called the Big Rip. It is not the leading expectation under the simplest models, but it remains one of the most vivid ways space itself could become destructive. In a Big Rip future, galaxies would first be torn from one another as expansion overwhelms the gravitational bonds between them. Later, individual galaxies would be disrupted. Stars would no longer remain held in their galactic orbits. Then planetary systems would fail as the expansion grew strong enough to pull planets away from stars. Closer to the final moments, planets, bodies, molecules, atoms, and even subatomic structures could be torn apart, depending on the exact physics. The horror of this scenario lies in the transformation of space from background into executioner. The distance between things would no longer be passive. Expansion would reach down from cosmic scales into local reality. Gravity, electromagnetism, and the forces holding matter together would lose their authority in sequence. The same phenomenon that once carried galaxies apart would eventually enter the scale of rooms, bones, oceans, and atoms. Scientists discuss this possibility because the nature of dark energy remains unknown. If dark energy behaves like a cosmological constant, the Big Rip does not occur. If it evolves in the right direction, the future changes profoundly. Observations continue to test this question, and recent surveys have raised the possibility that dark energy may not be perfectly constant. The evidence is not final, and the simplest picture remains powerful, but the uncertainty matters. The fate of all space may depend on a property of the vacuum we do not yet understand. A Big Rip would answer the question brutally. Space would end by becoming unable to hold anything together. It would not need an outer boundary, because every boundary inside it would fail. The edge would arrive everywhere, from the largest cluster to the smallest structure, as expansion made separation absolute. For many years, one of the classic possible endings was the Big Crunch. If the universe contained enough matter, and if gravity could eventually overcome expansion, then the outward motion would slow, stop, and reverse. Galaxies would begin moving closer again. The universe would contract, temperatures would rise, the cosmic background would grow hotter, structures would collide, merge, compress, and finally disappear into a dense, fiery state that might resemble the beginning in reverse. Current observations of accelerated expansion make a simple Big Crunch less likely under the standard model. Dark energy appears to push the universe toward continued expansion rather than recollapse. But the question is not closed, because dark energy's nature remains mysterious. If it weakens, changes sign, or evolves in ways not captured by the simplest model, cosmic contraction could return as a possibility. Recent observational programs mapping millions of galaxies aim to test whether dark energy has changed across cosmic time. The Big Crunch has a strange symmetry. It offers an end of space by reversal. Distances shrink, horizons change. The great separations built by billions of years of expansion begin to close. A future observer might see the sky grow brighter and more crowded as galaxies return. But such an approach would not be a reunion in any gentle sense. It would be compression, heating, collision, and loss of stable structure. Near the final stages, the universe would become hostile to complexity. Galaxies could no longer preserve their forms. Stars and planets would be overwhelmed by rising radiation and density. The distinction between separate places would dissolve as the scale factor collapsed. In this vision, space does end, not by fading into cold emptiness, but by losing room. The distances that once allowed structure, orbit, and history would be crushed out of existence. Some speculative models imagine a bounce after such a collapse, a new expansion born from the end of the previous one. These ideas remain far beyond certainty. They belong to the frontier where cosmology meets quantum gravity, a field still searching for a complete theory. If a bounce exists, then the end of space may be a transition rather than a final silence. But from within any one universe, the crunch would still be an ending beyond survival, memory, and continuity. There is a more alien possibility, one that does not require stars to burn out, dark energy to rip matter apart, or gravity to reverse the universe. It comes from quantum field theory and the nature of the vacuum itself. What we call empty space is not simple nothingness. It is a physical state with fields, fluctuations, energy, and laws. The vacuum has properties. It can be stable, or perhaps only metastable. If our vacuum is metastable, it may resemble a valley that is low enough to seem permanent, while a deeper valley exists somewhere beyond a quantum barrier. In that case, a transition could occur through quantum tunneling. A bubble of lower energy vacuum would form and expand at nearly the speed of light, rewriting the laws of physics inside it. Particles, forces, chemistry, and matter as we know them could cease to function. There would be no warning, because the bubble wall would arrive almost with the light announcing it. This scenario is known as vacuum decay. It is deeply speculative, and there is no evidence that such an event is imminent or inevitable. The current universe has already survived for billions of years, and calculations depend on physics at energies far beyond ordinary experiment. Still, the idea is scientifically meaningful because it treats space not as a blank absence, but as a state that may have structure and vulnerability. Vacuum decay would make the end of space local at first, then universal in spread. It would begin somewhere, perhaps anywhere, then expand outward, converting the vacuum as it moved. Unlike heat death, it would not wait for stars to age. Unlike the Big Crunch, it would not require the universe to reverse. Unlike the Big Rip, it would not tear through structures by expansion. It would change the rules that allow structures to exist. The unsettling part is that no observer could prepare. The event would outrun any possible alarm. There would be no approaching glow in the sky, no ancient prophecy written into the motion of galaxies. One moment, the familiar vacuum would support atoms and light. The next, the meanings of atom, light, and familiarity might vanish. Space would end by becoming another kind of space, one in which our form of reality has no foothold. Black holes offer another kind of ending, not for the universe as a whole, but for regions inside it. A black hole forms when matter collapses so intensely that an event horizon appears, a boundary beyond which future paths lead inward. From outside, the horizon marks the limit of return. From inside, the singularity, or whatever quantum gravity replaces it, lies in the future of every falling object. Space and time exchange roles in ways ordinary intuition cannot follow. In this sense, black holes create local endings of accessible space. A traveler crossing the event horizon of a large black hole might notice nothing special at the boundary itself, but the crossing would be irreversible. Every possible path ahead would lead deeper. The outside universe would remain real, but no signal from the traveler could return to it. The black hole is therefore a place where space does not end as surface, yet all outward futures end. For the larger fate of the universe, black holes may become the final great structures. After stars die, after galaxies fade, after ordinary sources of light diminish, black holes could remain for immense stretches of time. They may slowly lose mass through Hawking radiation, a quantum process by which black holes emit faint thermal radiation. For stellar and supermassive black holes, this evaporation would take times far beyond the current age of the universe. A universe dominated by black holes is one where space still contains depth, gravity, and hidden interiors, but very little visible life. Eventually, if Hawking radiation is correct, even black holes evaporate. The last great reservoirs of mass would leak away into faint particles and radiation. The final black hole deaths would be among the last energetic events in a universe otherwise ruled by darkness and dilution. Here, space ends in layers. It ends locally, at horizons. It ends historically when black holes become the final monuments of collapsed structure. It ends thermodynamically when even those monuments evaporate. The black hole is therefore both an object and a prophecy. It shows how a region of space can be cut off from the rest of reality, and it hints at a far future where almost everything becomes either unreachable, invisible, or gone. The phrase "outside the universe" is seductive, but it may be meaningless. In ordinary speech, every object has an outside because it exists inside a larger space. A box has an outside because the room surrounds it. A planet has an outside because space surrounds the planet. But if the universe means all of space-time, all physical relations, all distances, all directions, then asking what lies outside it may be like asking what is north of the North Pole. The grammar survives after the geometry has failed. This does not mean the question is foolish. It means the question may need translation. When people ask whether space ends, they may be asking whether the universe has a boundary. They may be asking whether reality extends beyond the observable region. They may be asking whether other universes exist, whether higher dimensions contain our cosmos, or whether the Big Bang emerged from some deeper physical state. Each version belongs to a different level of speculation. Some theories propose a multiverse, where our observable universe is one region among many, perhaps produced by inflation, quantum branching, or higher dimensional physics. These ideas are fascinating but difficult to test. They may one day gain support through indirect evidence, or they may remain beyond empirical reach. A responsible script about the end of space must hold the distinction carefully. The unknown is not empty. It is also not permission to claim certainty. If space has no outside, then its end cannot resemble the edge of an object. It must be described from within by curvature, topology, expansion, horizons, temperature, entropy, or the breakdown of physical laws. We are inhabitants of the geometry we study. We cannot step outside the universe, turn around, and photograph its outline. All our knowledge arrives through signals moving inside space-time. There is a quiet humility in this. The greatest maps ever made are still interior maps. Every telescope, every equation, every particle detector, every deep field image is an act performed from within the thing being measured. If space ends, we may never see the ending as an external shape. We may only infer it through the behavior of light, matter, and time. Distance is one of the oldest human experiences. A child reaches for a hand. A traveler crosses a road. A sailor follows a star. Civilization is built from the effort to overcome separation. Roads, ships, radio, rockets, language, mathematics, and memory are all ways of making distance less absolute. Space becomes meaningful when it can be crossed, measured, signaled through, or imagined as part of a shared world. Cosmology teaches that distance has deeper categories. Some distances are difficult. Some are impossible in practice. Some are impossible in principle. The moon is distant, but reachable. The nearest stars are almost impossibly far by current engineering, yet still inside the same broad cosmic neighborhood. Distant galaxies are visible but unreachable. Regions beyond our horizon are neither visible nor reachable. They may exist, but they cannot belong to experience in the same way. This layered distance changes the emotional meaning of space. The universe is not one open arena where patience eventually wins. It is a structure with causal boundaries. There are places whose ancient light can move us, though no future action can affect them. There are places that may be real yet forever absent from our sky. There are futures in which the sky itself will lose the evidence of its own depth. So perhaps space ends first as a relationship. It ends where cause and effect can no longer travel. It ends where a signal cannot arrive, where a journey cannot close, where an event cannot be witnessed even in principle. This kind of ending is less theatrical than collapse or fire, but it may be more relevant to any living mind. A universe beyond all possible contact is, for us, less a destination than a mathematical shadow. Still, the shadow matters. The knowledge that unreachable regions exist changes how we understand our own. It prevents us from mistaking the visible for the whole. It reminds us that humility is not a poetic ornament attached to science. It is a technical requirement. The universe is larger than the evidence it can deliver to any single location. Before reaching the human scale, there is one more difficulty to face. Space may not have the same shape at every level of thought. The part we observe looks remarkably smooth and flat on the largest measurable scales. But the universe could still possess a global form hidden beyond the visible horizon. A tiny patch of a vast curved surface can look flat to a creature living on it. In the same way, our observable universe may be only a region of a geometry too immense for our instruments to resolve. This is where topology enters the question. Geometry describes curvature, but topology describes connectedness. A universe could be flat and still finite if its space wraps around itself in a complicated way. In such a cosmos, a beam of light traveling far enough might theoretically return from another direction, though cosmic expansion, finite time, and practical limits could make this impossible to observe. The idea is difficult because it asks the mind to imagine a space without a wall, without a center, and perhaps without a unique outside. It is a shape that cannot be held in ordinary visual memory. Astronomers have looked for signs of such wrapping in the cosmic microwave background, searching for repeated patterns in the oldest light. So far, no clear evidence has shown that our universe closes back on itself at scales we can see. But absence of evidence at our horizon does not settle the question. The universe could be far larger than the observable region. Its global shape could remain forever hidden if the identifying patterns lie beyond the light we can receive. This matters because an end of space may be impossible to picture with ordinary images. A finite universe with no edge would not present a border where the stars stop. It would present a complete geometry, self-contained from within. A traveler would not strike a cosmic wall. The journey would be governed by curvature, expansion, and time. The end would be encoded in the total shape, not in a final visible surface. The old dream of finding the last place in space may therefore belong more to mythology than physics. The universe may be boundless in movement, finite in volume, infinite in extent, or simply too large for the distinction to become visible from our position. The deeper lesson is that space has forms beyond the reach of common sense. It may end mathematically while never ending as a road. To ask about the end of space also forces us to ask what kind of beginning space had. The Big Bang was not an explosion into a pre-existing void. It was the early, hot, dense expansion of the universe itself. Every observable region was once compressed into a much hotter and denser state. Space did not wait outside this event like an empty room waiting for matter to enter. Space was part of the event. This point is essential because many false pictures of the cosmic end come from false pictures of the cosmic beginning. If the Big Bang were a detonation in darkness, then one might imagine debris spreading into an outer emptiness until it reaches a frontier. But the universe is not known to be expanding into anything. Expansion means that distances within the universe change. The metric grows. Galaxies become farther apart where they are not gravitationally bound. The scale of space evolves from inside the system. The earliest moments remain incomplete in our understanding. General relativity describes gravity and cosmic expansion with extraordinary success, while quantum physics describes particles and fields with equal power. But at the beginning, when densities and energies become extreme, the two languages must meet. A full theory of quantum gravity remains missing. This uncertainty leaves open profound questions. Did space truly begin, or did our current expansion emerge from an earlier state? Was there a bounce, an inflationary phase, a quantum transition, or something no current model can fully express? The end may depend on the answer. If the universe began from a quantum gravitational state, its final destiny might also require quantum gravity to understand. If dark energy changes, the future may diverge from the simplest picture. If the vacuum is metastable, the laws beneath space may shift. If cosmic inflation produced regions beyond our horizon, our visible universe may be only a local history inside a wider process. The beginning is not only a vanished event, it is a clue about what space is made of. There is something humbling in the symmetry of ignorance. We can describe the universe from fractions of a second after the beginning to billions of years of cosmic evolution, yet the first instant and the final destiny remain veiled. The two great edges of cosmology, origin and fate, are connected by the same question. Is space fundamental, or is it something that emerges from deeper physics? If space is emergent, then its end might be less like the destruction of a place and more like the failure of the conditions that make place possible. One of the most haunting futures is not the death of all matter, but the death of evidence. The universe may one day become a place where intelligent observers can no longer reconstruct the story that made them. They may live in the remains of the local group after the Milky Way and Andromeda have merged into a single great galaxy. Around them, the distant universe may have slipped beyond the cosmic event horizon. The night may be deep, quiet, and strangely local. Such observers might still discover gravity, atoms, stars, and planets. They might build telescopes larger than cities. They might measure the motions of nearby stars with exquisite precision. But the grand evidence for cosmic expansion could be gone from their sky. Distant galaxies, once visible in all directions, would have faded beyond detection. The cosmic microwave background, stretched by expansion for unimaginable ages, would be colder, weaker, and harder to distinguish from other faint signals. The universe's origin story would become harder to read. This is a different kind of cosmic loss. It is the loss of context. A civilization can be scientifically brilliant and still inherit a poorer universe. Its instruments may be superior to ours, while its sky contains fewer clues. It may live later in time, but earlier in understanding because the evidence has passed beyond reach. The cosmos does not preserve its records for every future observer equally. In our age, the universe is unusually generous. We can see galaxies in every direction. We can detect the cosmic microwave background. We can measure expansion through redshift. We can infer dark matter from gravitational structure and dark energy from accelerated expansion. We live at a time when the universe is old enough to have created complexity, yet young enough for its largest patterns to remain visible. That balance may be temporary. The end of space, then, may arrive as amnesia. Not total darkness, not instant ruin, but the slow erasure of evidence from the observable world. The sky will still exist, stars will still shine for a time, but the record of the wider cosmos will fade. Future minds may ask whether space continues beyond their island and receive only silence where we once received light. Empty space is often imagined as nothing, a blank interval between stars, a gap without weight, texture, or consequence. Modern physics has made that comfort difficult to keep. The vacuum is filled with fields. It has quantum fluctuations. It can possess energy. It participates in expansion. It may even determine the ultimate fate of the universe through dark energy or vacuum stability. The emptiest thing we know may be one of the most powerful actors in existence. This changes the emotional force of the question. If space were only absence, then its ending would be difficult to imagine. Absence cannot easily break. But physical space is not a passive void. It has rules. It can curve around mass. It can stretch between galaxies. It can contain horizons. It can carry radiation from the early universe across billions of years. It can decide which events belong to each other through causal structure. The vacuum is quiet, but quietness should not be mistaken for simplicity. Even the darkness between galaxies has a history. It has cooled with the expansion of the universe. It has been crossed by ancient photons, gravitational waves, neutrinos, and perhaps particles from events long vanished. It has hosted the growth of cosmic voids, enormous regions where matter is sparse and galaxies gather mostly along the surrounding filaments. These voids are not errors in the map. They are part of the map's architecture, vast hollows shaped by gravity and expansion across cosmic time. In the far future, these voids may become the dominant emotional image of the universe. Galaxies outside bound structures will recede beyond contact. Local remnants will age. Radiation will dilute. The background temperature will fall. Space will become emptier in every practical sense, though never simply equal to philosophical nothingness. It will remain a physical condition, stretched thin across time. This is why the end of space cannot be reduced to the disappearance of matter alone. Matter may fade, decay, or become locked in remnants, but space carries the final arrangement. It is the field in which entropy plays out. It is the distance through which signals fail. It is the cold volume where ancient structure becomes memory. Empty space is not a blank afterword to cosmic history. It is one of the main characters. Any story about the end of space contains an observer hidden inside it. We ask what would be seen, what would be known, what would remain. But in the deepest future, observers themselves become uncertain. Life as we know it depends on stars, chemistry, gradients of energy, and stable environments. Intelligence requires not only matter, but time, memory, and usable power. A universe drifting toward heat death becomes less friendly to all of these. Speculative civilizations might attempt to survive by adapting to colder conditions, slowing their processes, harvesting the last stars, using black holes as energy sources, or spacing their thoughts across immense intervals. These ideas belong to the borderland between physics and imagination, but they reveal something important. The end of space is never only a question of geometry. It is also a question of whether any process remains capable of noticing geometry. If all observers vanish long before the final physical state, then the experiential end of space occurs earlier than the thermodynamic end. The universe may continue expanding for times beyond comprehension, but without eyes, instruments, memory, or computation, there is no perspective from which distance has meaning. Physics may still describe the state, but experience has left the cosmos. This does not make the later universe unreal. It makes it alien to the categories by which humans understand endings. We imagine endings as witnessed events, the final light, the last sound, the closing horizon. But the deepest cosmic ending may have no witness. The last observer may disappear while space still has an almost endless future ahead of it. There is a difficult beauty in that thought. We are not close to the final age of the universe. We are early enough to see the great structures, early enough to ask, early enough to preserve a record of what the cosmos looked like while it was still bright. Perhaps this is one of the rare duties of intelligence, to notice the universe during the interval when noticing is possible. Human beings ask whether space can end because we are finite creatures surrounded by an apparently infinite dark. Our lives are brief, our senses local, our bodies fragile. Yet the mind can extend itself across billions of light years through mathematics and light. We can speak about horizons no spacecraft will reach, about epochs no species may survive to witness, about futures in which every star now visible has died. This is one of the stranger achievements of consciousness. A temporary animal can contemplate the exhaustion of cosmic time. The answer to the question is not single. Space may have no edge. The observable universe has a limit. The reachable universe is smaller than the visible one. The future sky may empty as expansion carries galaxies beyond contact. The stellar era will end as fuel is spent. Heat death may leave a vast, cold, thin cosmos where little can happen. More speculative futures offer rupture, collapse, or vacuum transformation. Each possibility describes a different meaning of ending. What they share is the destruction of a simple intuition. Space is not merely a dark container. It has history. It has dynamics. It has horizons. It can stretch, cool, isolate, hide, dilute, and perhaps transform. The distances between galaxies are not passive emptiness. They are part of the universe's fate. The blackness above us is not an inert background behind the stars. It is a physical participant in the story. And for now, we live in a rare age. The universe is old enough to contain heavy elements, planets, oceans, and mines, yet young enough for the galaxies still to be visible in abundance. The cosmic microwave background still carries its ancient message. The night sky still contains clues to the beginning. We can still see enough of space to know that our island is not alone, even if many of those distant islands are already beyond reach. If space ends, it may not end where imagination first looks. It may end at a horizon, in the loss of contact, in the fading of stars, in the exhaustion of usable energy, or in a change to the vacuum beneath all things. The final answer remains uncertain because the universe has not finished revealing what it is. But the question itself has value. To ask whether space can end is to recognize that even emptiness has a destiny, and that the dark between stars may be one of the most fragile things we have ever named.